Hello everyone, welcome to my channel, welcome to Engineering. My name is Andrew. Hopefully everything is setting up nicely. Welcome, my name is Andrew. I am currently a PhD student at UCR. I study chemical and environmental engineering, and we're doing a live stream. So I'm here to help you all out during these times, during Zoom University. What we're going to do is we're going to do a study with me. So as y'all are coming in, we're going to study for approximately 45 minutes, try to get into the flow state, and then please ask your questions. Ask your questions as you guys are entering, and then I'll be sure to answer as many questions as I can as we move forward with this live stream. So I think what I'm going to do is send out this link to everyone. Please let me know if there's any technical difficulties, things like that. So far everything seems good, right? You can hear me. That's all that matters. And I'm going to go ahead and send out this link. So if people are coming in, then go ahead and let me know. Otherwise, I'm going to go study. I'm going to go study for my classes. And then at 7 p.m. PST, we're going to do a workshop. This is going to be the first of a series. I really want to turn this into a series in which we talk about chemical engineering, almost like a podcast style, but also a mix of a lecture because it's also live. I don't know. We'll see how this goes. It'll be fun. And yeah, see how this goes. So I'm sending out this link to my friendsies and my mom and my family. And then as y'all are hopping in, then please drop your questions. So again, at 7 o'clock, we're going to do a workshop. So I'll talk about chemical engineering and just do an intro overview, just chemical engineering, what I want to do on this channel, and begin to answer your questions. And then at 8 p.m., we're going to do office hours. So you're going to be free to ask anything you want. Okay? So hopefully this is set up nicely, and if there's a decent amount of people, then maybe we'll do this regularly, maybe bi-weekly. I don't know. We'll see how this goes. Alright? So I'm just sending out this link because ain't nobody going to be watching this unless the YouTube algorithm does me the favor of sending this out. Alright, I'm just going to IG this. Okay. Yes, let's go. Join the live stream. Okay, we have lots of links on the side, so including my mom and her TikTok. So check out my mom's TikTok. She's quite active. Actually, let me adjust this slightly, just to get rid of those zoom bars. That's better. That's better. All right. Welcome to the one viewer. That's probably, I'm guessing, my mom. Join the live. Link in bio. Okay. So again, if you have questions about chemistry, physics, anything chemical engineering related, I'll do my best to help y'all out. Okay, let me know what classes you're taking. Also, there's a survey, so please check out the links because there's gonna be a survey. So I'm gonna be definitely looking at those. Hopefully that works. I'm also gonna check if that works. And then we're going to do this together, right? So I'm gonna see if the survey is okay. All right. Yes, I think it seems everything's good, but the volume is a little strong, right? We're learning together. This is gonna be a new thing. I think we might like this. Okay, the survey. So there's lots of links. Hopefully you can see that. Okay. There's lots of links down there. And then also a giant list of resources. Alright, I'm going to go ahead and get started on my studies. I'm gonna go ahead and just let y'all hop in. And let me just put this link in my bio. So I'm gonna study for about 45 minutes. I'm not gonna read any messages yet, but please join your. Please leave any comments. Questions, and then I'll get back to all of y'all's questions. The audio, is this slightly better? Hopefully this is better. We'll see. We'll try it out. We're all learning together. Okay. So I'm going to get in the flow state, and I'm going to read some books. I think I'll be reading currently my favorite book, which is Transport Phenomena. And that will prime my brain for answering the chemical engineering questions, because I have no idea what y'all are gonna ask me. So let's just get started. was wondering if I should, but copyright, you know. I'll do copyright free music. Copyright free. Okay, let's try this. Okay. Is this better? I hope that this doesn't end the stream right now. Okay, I'm gonna leave it. Let's see if that works. All right. How's it going? That was about 45 minutes. How was that? Was that long? Was that a really long study session? Okay. I think we're gonna start the actual part of the live stream now. So currently there's a few of you joining in. Thank you everyone. Did anyone study along with me, or was it just me for those 45 minutes? Okay. I think there's some delay. I'm gonna have to fix that for next time. So, if you're just joining in, thank you so much. My name is Andrew. I'm a grad student at UCR. I study chemical engineering. So on this channel, it's all about chemical engineering. But I also want to, since this is a live stream, and I have no idea what kind of audience this is gonna be, right? So I want to encourage everyone else to help facilitate everyone else as they're joining in. You know, help answer questions like technical difficulties. We're gonna try to condition everyone else that's joining in to, we're gonna have this like mind frame of like professionalism. I want to come across that professionalism is one of the main keys. I was a part of this organization called the Society of Hispanic Professional Engineers, and it's called SHIP, Society of Hispanic Professional Engineers, and SHIP is all about professionalism. So if you're just tuning in, we have lots of links for my YouTubes. I have my main account, which is this is what you're watching right now. You can follow me on YouTube, subscribe to my YouTube, and also my new account. So my new account is gonna be more like less fun stuff, more professional, and more lecture based. And then here is just gonna be a mix of everything, because as YouTube changes over the years, it's just gonna be anything. Also, my mom is joining us. Check out her TikTok. She does TikToks all the time. So please, as you guys have questions, please let me know what kind of questions I can answer. And then for the next like hour or so, we're gonna do, or for the next few minutes or so, we're gonna do a workshop just to kind of say what this is all about, because I think I have a vision of how to help y'all, because a lot of you guys are asking for all kinds of stuff. On TikTok, there's mostly like high schoolers asking more like specific chemistry questions, and then on YouTube it's more like chemical engineering, and then on Instagram it's more like tips. So all these like different social medias are like combining and mixing, and I think that this live stream thing is gonna be like, it's gonna be one good study session for me, just reviewing, and we'll see how this goes during these times, because we're all still chilling at home all the time. So I'm gonna talk about chemical engineering for a while, and then as soon as you guys have questions, please let me know, and then I'll be sure to get through as many as I can throughout the rest of this live stream. So we're going to talk about, where are we? We're going to talk about chemical engineering. So like I said, we have two channels. So my main channel is engineering, and then my newest channel is going to be mostly like chemical engineering lectures. So it's going to be a little bit difficult for me to lay a foundation of how to build a curriculum, because I'm still in grad school, and so I'm still learning things myself. But I understand that chemical engineering can be really difficult, and so I want to try to build a curriculum. I think it's possible to learn everything about chemical engineering online. At least in terms of the math and the fundamental principles, you can learn all of chemical engineering online. So based on other YouTubers like Khan Academy, MIT OpenCourseWare, Patrick JMT, those are the folks that I watched when I was an undergrad. But they have a lot of the fundamentals, like a lot of the math, but there's not really too much for chemical engineering. There's chemical engineering guy, he's great, check him out. There's the Learn Chemie, but there's not too much else. And also, if you think about it if you zoom out from the grand picture of things, the internet is still quite young. The internet is still quite relatively young if you zoom out. It's definitely been pervasive in my life, and many folks in my generation have definitely been influenced by the internet. Gen Z is known as like the internet generation, but it's still really, really new, and that's scary because technology can take over, but it can also be good. So I believe that chemical engineering can be learned online in terms of the fundamentals. So we're gonna try to do that on this channel, and especially like ramp it up now, because with Zoom and everything, it's just like not fun. So here's me. I do research, and so my research is water treatment, in particular photochemical denitrification. So that's a fancy way of saying that I use powerful lights to turn bad water into good water. Okay, so I like to travel, despite COVID and everything, and one of my best tips for college and studying and engineering is you gotta make friends. You gotta make friends, because those are the people that are gonna like help you carry during your studies, during your own study sessions. So you gotta make friends. So those are me and my friends during graduation. Okay. And another tip is, it's not what you know, it's who you know. Okay. So that means networking. Networking is gonna be one of the main things in chemical engineering. In engineering in general, you have to learn how to network with each other, be professional, be proactive at reaching out to other people and building your network from the ground up. Okay. So I have a survey. I don't know who's still here. If you can go ahead and click the link in the description, it says survey. Let me know, and then I'm just gonna leave that open like forever. See if anyone checks that out. Otherwise, I'm gonna see, like how many people are like interacting with this channel, and then we can do lots of really fun activities based on based on those responses. All right. Also, a list of resources. So again, check out the links in the description. I really want to build a giant list of resources. So I'm going to take a screenshot of what it looks like currently. And let me pull that up. So I think that there's a lot of general stuff out there, but it's kind of hard to consolidate everything with so many resources, so many TikToks, so many YouTubers in chemical engineering. So we need to kind of consolidate and then help each other, put it out there. So here's what it looks like. I'm going to put it right here. I'm going to take a screenshot. It looks like this. All right. We're going to make a giant list of resources and then try to help each other. So if you think that like, okay, Khan Academy helped me a lot with understanding physics, understanding chemistry, then like definitely put Khan Academy. If you think that like I don't know, your favorite resources that help you during your studies, or like your favorite books, your favorite websites, things like that, things of that nature. All right. What is next? Professionalism, okay, and chemical engineering in a nutshell. So now I'm going to talk about chemical engineering. There's a lot to it, so I'm just going to be describing as much as I can, and I think that I can try to explain some of the basic principles and then put those in like one nice piece of like one nice equation, if you will. You'll see what I'm talking about. Okay, so chemical engineering. There's a lot of different branches of chemical engineering. There's a lot of branches of engineering in general. There's chemical engineering, of course, civil engineering, electrical, and mechanical. So with chemical engineering, there's like the principles of applying chemistry and physics to solve problems or to produce chemicals on a large scale and develop those for real systems. And then, civil engineering, that's a little bit more like, let's say, common knowledge. So civil engineering, you're going to be building things. You're going to be trying to save money on materials and costs to build things effectively and make sure that they don't move. I like to say that civil and mechanical engineering are kind of like opposites, because a civil engineer's job is to make sure that things don't move, and a mechanical engineer's job is to make sure that things do move properly. So mechanical is going to be building more things like cars, like an Iron Man suit, and then civil engineering is going to be like building really cool buildings. And then with electrical engineering, that's using like electrical systems, like circuits. You can make your own circuits, make your own computers. So now there's different branches of everything else. So with chemical engineering, there's branches off of chemical engineering to make other things like environmental engineering. And then the branches of electrical engineering might be like computer science and computer engineering, right? All right. And so I like to say that chemical engineering is taking math, science, and physics, math, chemistry, and physics, calculus, chemistry, and physics. You're putting those in a bowl and you're mixing it all together, and then you're getting one nice new system, and that system is going to be your major, which is chemical engineering. So it sounds scary because it's kind of like studying 3 majors in one. It's kind of like studying calculus. You're kind of like a math major. It's also studying physics. You're also going to be studying lots of undergrad and grad level physics, and then also chemistry. You have to know chemistry really, really well. So combining all 3 of those, generally it seems scary. It does, because there's a lot that goes to it. But each of these 3 fields can be incorporated into one giant field, which is chemical engineering. But that is to say that chemical engineering is not the 3 of these. It's separate. It's its own separate field. It's a branch of engineering, and engineering is not necessarily science. Science and engineering are similar because they both apply the principles of science, but science itself is more investigating the properties and nature of the world to understand the world we live in, and engineering is using those principles and apply them to solve problems, right? So with chemical engineering, you're going to be using all these principles, combine them together, and then try to figure out how to produce chemicals on the mass scale, figure out how to solve environmental issues, clean water, clean the air, clean the atmosphere, you can make a magic device that captures CO2 in the atmosphere. Did you know that Elon Musk is going to pay people millions of dollars, either from his own pocket or from his company's pocket? He's going to pay people millions of dollars to capture CO2 from the atmosphere. A chemical engineer perfectly fits that role, fits that description, because the chemical engineer can figure out how to extract the CO2 and then convert it to something else that's more useful. Maybe some other carbon-based substance, turn it into fuel, turn it into something more profitable. And it is indeed a challenge because there's a lot of CO2 in the air. So you're kind of going to be killing two birds with one stone, because on one hand, you're going to be capturing the CO2 in the atmosphere, and then on the other hand, you're going to be converting the CO2 and then producing another chemical, which you can sell. Hint, hint, wink, wink, wink. That means that chemical engineers typically make a lot of money. That's another reason maybe chemical engineering is something that you could do. All right. So there's a lot to go over, and so I kind of want to talk about like a branch of all of these three. So the chemistry, we need the periodic table, and then we're going to need the conservation of mass, conservation of energy, conservation laws. There's also conservation of momentum, and then something called dimensional analysis. All right. And then with physics, have you heard of vectors and Newton's laws, classical mechanics, and then thermodynamics? Okay, those three concepts from physics and or calculus, but also calculus itself. So with calculus, you really need to understand functions. Also pre-calculus, understanding the concept of the limit, and derivatives and integrals, the relationship between the two. So raise your hand if you know what is a derivative or an integral. Unfortunately, I can't interact with y'all in that sense. There's no way to like raise your hand, right? Anyway, so some may think that this stuff is too easy, and some may think that this stuff is really difficult. So please let me know, if you're watching this or on my channel, let me know recommendations for what you want to see, and then I'll be sure to like try to answer those questions carefully and then help you understand, get up to speed. Because I don't know if you're in high school, you're struggling with chemistry, or you're in college, you're doing all right with your classes. I don't know. Homework, it's obviously optional, but if I tell you to do a problem, then you should probably do it, because it's going to be like really helpful for you to understand these fundamentals. All right. So the first thing, very first thing you have to understand is the atom, which consists of protons, neutrons, and electrons. And atoms are tiny little balls that are mostly empty space, and they consist of stuff which has reactions, except everything I just said is not true, because atoms are not tiny little balls, and the electron is not swirling around the atom like a little ball, like a little... See, that's what I thought it was when I first heard of atoms. Electrons are both particles and waves, which means that they follow wave mechanics, which means that we need quantum mechanics to describe electrons. Okay, on this channel I won't be talking about quantum, at least for a very long time. Maybe I'll do some physical chemistry in the future. So typically chemical engineers don't always need to study quantum. Some do. Some chemical engineers do need quantum mechanics if they want to study the electronic properties of chemicals and their systems, especially at the nanoscale. But at the undergrad level, we don't need too much quantum mechanics. So we're going to pretend that atoms are little balls, and they fly around and jump around in the nucleus, and they do all these crazy magical behaviors called chemistry and physics. All right? So what do we know about the mass of the nucleus and the mass of the proton, the mass of the neutron? Okay, pop quiz. What element are we looking at here? If there's 2 protons and 2 neutrons in the nucleus, we are looking at helium atom. Okay, so the mass of one proton is 1.67 times 10 to the minus 27. That's a really small value for the mass. That's almost incomprehensibly small value for mass. It is 10 to the minus 27 kilograms. So 2 of those is going to be 2 times 1.67 times 10 to the minus 27. The mass of the neutron is approximately, it's very, very close to the mass of the proton. So we're going to say that they're pretty much equal. The mass of the neutron is also 1.67 times 10 to the minus 27 kilograms. Those are very, very small masses. The mass of the electron is even smaller. It's 2,000 times smaller than both of those. Okay, so the atomic mass unit is going to be our conversion factor for counting up all these atoms. In your body, there's billions and trillions of atoms swirling around, making up your survival. And so we need Avogadro's number. Avogadro's number is going to be a very large number because there's a very large number of atoms in 1 mole. What is 1 mole? It's going to be 6.022 times 10 to the 23 things or atoms. That's a very, very large number. Okay? And we can also know the radius at this approximate scale. It's going to be about 1.4 angstroms, 1.4 times 10 to the minus 10 meters. Okay? Keep that in the back of your mind. If you're going to memorize one thing, memorize the periodic table. It's going to be the entire curriculum in undergrad, but especially those circled elements: hydrogen, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, phosphorus, sulfur, chlorine, potassium, and calcium. Especially if you work in water, those are going to be the top, the most important elements you need to memorize. And what do I mean by memorize? I mean you need to memorize first of all, the chemical symbol. That's number 1. Second of all, the atomic weight, but also try to memorize the atomic structure. What does this atom look like? What does this consist of? What are these properties of the system? And try to understand as much as you can as possible. Alright. Now we're talking about conservation laws. Mass, energy, momentum, and charge. Those are 4 conserved quantities that mass cannot be created or destroyed, energy cannot be created or destroyed, and momentum cannot be created or destroyed. And also charge cannot be created or destroyed. So charge is based on the electrons, so we don't deal with charge as much as the electrical engineers, but we definitely deal with mass, energy, and momentum quite a lot. So what does that mean? It means that if I put 3 balls in a box, if I put 3 balls in a bucket, and nothing happens to them, there's no reaction or anything, then there better be 3 balls in that bucket as soon as I open it up, right? So that means that conservation of mass, conservation of energy, they're really useful tools for deriving calculations. And in fact, these 3 equations you see on the right, the momentum, energy, and mass balance, mass flux equations, those are going to be extremely useful for your advanced engineering classes. Alright? Unit conversions. There's no easy way around this. You're just going to have to practice it. So your first, quote, homework assignment, right, is to use the internet and a calculator and your brain to calculate the number of atoms, protons, and neutrons in 100 kilograms of water. Okay, so imagine you have 100 kilograms of water. That's a lot of water, actually. That's like 200 pounds of water. Okay, that's a really, really large amount of water. So there's gonna be a lot of atoms in that system of water. But also calculate your age in seconds. So how old are you? Let's say Barack Obama. I don't know. How old is he? Some arbitrary age. Let's say 36 years. How do you convert 36 years into seconds? So first you got to multiply 36 years times what, 365 days, and then convert days to hours, and then minutes, and then seconds. Okay, so multiply that value. It's going to be a really large value. And then the distance from the Earth to the Sun. So you can look up, it's probably going to give it to you in miles on Google, right? Look up the distance from the Earth to the Sun in miles, and then convert that to inches. So how many feet are in 1 mile, and then there's 12 inches in a foot, right? So then you're gonna have to cancel out or multiply some of those values. So notice how the first one is calculating a mass quantity, the second one is calculating time, and then third one is calculating a length quantity, the length quantity. All right. So mass, time, and length. Those are three of the fundamental base dimensions: mass, length, and time. Okay, the fundamental base dimensions. All right. So we're talking about dimensional analysis. So dimensional analysis is basically this magic tool set that we can use to derive almost everything in physics and engineering. So like I said, we're going to have mass, length, and time, which is going to be given by the variables m, mass, length, and time. So mass is lowercase m for the variable, and it's in units of kilograms for SI units. So let's say 3 kilograms, 10 kilograms. And then the unit name is in kilograms. The dimension is a capital M. All right. Also, I want you to know if it's a vector or scalar, which we haven't talked about yet. But if you know what is a vector or scalar, try to understand if it's a vector or scalar. A scalar is just a number. All right. So mass is just a number, has no direction quantity, so therefore it's just a number. It's just a scalar. But length, however, so length is going to be given by the variables x, y, or z, and the SI units are in meters. It's an m, but don't confuse the m meters for the m in mass. Okay, so the m in mass is the variable, but the m in length is the SI units, which is meters. All right, so the dimension is going to be capital L. All right, and it's a vector or a scalar. So we're going to have to define what is a vector if I want to explain that. And then also time. Time is going to be measured in seconds. So the unit name is going to be in kilograms, or excuse me, the unit name is going to be in seconds. And it's going to be, the dimension is capital T, or it could be lowercase t. Some texts like to interchange those two. And that is also a scalar. Okay? So, based on understanding, we can combine these three. Well, there's going to be more base dimensions. There's also temperature, electric current, luminous intensity, and amount. So all of these are extremely useful because they can derive all of physics. Now we can derive pretty much everything else. We can derive area, volume, speed, velocity, acceleration, momentum, force, energy, pressure, flux. All these quantities are going to be used extensively throughout undergraduate and graduate level science and engineering. So if you're studying Newtonian mechanics, you need to know all about forces, all about momentum, all about velocity and acceleration. And then as you go more advanced, you can define what is flux. Okay, what I want you to do is to understand what these dimensions are, right? And then understand if it's a vector or scalar. For example, force is a vector because it can be defined by an arrow. A vector is just an arrow, has a magnitude and direction. And the direction is indicated by the arrow, just like this pen. This pen could be a vector. The pen is an arrow. That's great. All right. So that's about like introductory, like just chemistry, just an overview of chemistry. Maybe some of you have been exposed to that. Maybe some of you that's new. So now we're going to talk about physics, which is Newtonian mechanics, Newton's laws. The concept of vectors, we're already talking about them, and then thermodynamics. Okay. So let's say we have this ball, and then we start to just move it around in space. Unfortunately, I don't think I'll be able to animate this live. Let's say the ball moves. Newton's first law states that an object in motion stays in motion unless acted upon by another force. So this ball is going to keep going on forever as long as no other forces interact with it. So if the ball is the only thing in the entire universe, then the ball will move on for the entirety of the universe. Next is going to be Newton's second law, F equals ma. Have you seen that before? So F equals ma is just the force, which is in newtons, is equal to mass times acceleration. All right. So again, if the ball now has a force, it's going to be accelerating. So accelerating is kind of like speeding up. But that's a really bad definition because we need calculus to define acceleration properly. All right. So now we have Newton's three laws. An object in motion stays in motion unless acted upon by another force. F equals ma is Newton's second law. And for every action, there is an equal and opposite reaction. So that means that if you punch someone in the face, it's going to hurt their face just as much as it's going to hurt your fist when you punch them. That's pretty interesting. Alright, now we can talk about vectors. So physics is about vectors and scalars. Scalars are just numbers. Vectors are arrows whose length is proportional to the value of the scalar number with a direction. Okay, so the vector is the magnitude, right? It's the length of the arrow in a particular direction, represented by the arrow itself. It's just an arrow. So it's very intuitive. Video games use vectors all the time. It's very intuitive. So if you have an arrow representing the force, if the vector is really large, then the force is really large. Okay, so we're gonna think about the length of the vector. So they're one-dimensional mathematical objects, and they're very useful because they can live in one-dimensional or two or three-dimensional space, or vectors can live in any dimensional space. That might be useful too. Okay, let's talk about the Pythagorean theorem real quick. Let's say we have this triangle, right? It has the bottom length is 4 and the height is 3. So we know based on the Pythagorean theorem that the hypotenuse, right? The hypotenuse is going to be 5. Okay. So how do I know that? Because we can count the squares. 1, 2, 3, 4 on the bottom. 1, 2, 3 on top. So that is going to be 4 on the bottom, 3 on top. That is going to be the Pythagorean theorem. We know the Pythagorean theorem is going to be the length of the hypotenuse is going to be the sum of the squares of the sides. Okay? And then we can define it on a coordinate system. So again, the bottom is going to be x equals 4. The height is y equals 3. Same thing. 4 squared plus 3 squared. Calculate it. Make sure I'm not giving you any wrong numbers. 3 squared plus 4 squared is 5 squared. So that's the Pythagorean theorem. That's the age-old theorem from ancient Greece. So this is a scalar quantity. It gives you the length of r, the hypotenuse r, if we solve this equation. But we want a vector. We want a vector that describes the length and the magnitude of that r. So what did I say vectors are? Vectors are just arrows. So we're going to define this vector. Okay, so now we're defining the vector r as just that length, just that magnitude of r. But now I'm giving it a little arrow. I'm giving a little tip on the arrow. Alright, so that little arrow is the vector r. Okay, so it can be described similar to a point 4, 3, but instead of a parentheses, we're going to use brackets. So the vector is given by the value 4 in the x direction and 3 in the y direction. Alright, so if it's 4 in the x direction and 3 in the y direction, we're going to know that in the r direction, again, we can use the Pythagorean theorem. How do we calculate that? Think about that. So now we have Newtonian mechanics. We define vectors. So an object in motion stays in motion unless acted upon by another force. But now look how I wrote Newton's second law. F equals ma. But now force is a vector. Why is force a vector? Because it has a little arrow on top of the F. That means that it's a vector. And mass is a scalar. Acceleration is also a vector. It's also a vector. So what is a vector? A vector is just an arrow. So if it has a little arrow on top, that means it's a vector. And what is a vector? It's a little arrow with a magnitude and direction that is proportional to the magnitude of whatever quantity you're looking at. And then again, for every action, there's an equal and opposite reaction. So see how we're combining math and physics and a little bit of chemistry? We're already starting to combine the three that I mentioned earlier. That's pretty neat. Now we're back to conservation laws because we're about to talk about thermo. So again, conservation laws state that stuff can't be created or destroyed. What kind of stuff? Mass can't be created or destroyed. Energy can't be created or destroyed. Momentum can't be created or destroyed. And charge cannot be created or destroyed. So using these principles, we can derive the laws of thermodynamics. So the Zeroth Law, it just exists just to exist. The Zeroth Law mathematically states that if A equals B and C equals B, then A equals C. So what does that mean? If you touch a hot plate and then the hot plate is touching another hotter substance, eventually eventually they're going to reach equilibrium. Eventually they're all going to reach the same temperature. Your skin and the hot plate itself, and then the other substance, eventually they're all going to reach a state of equilibrium. The first law states that energy cannot be created or destroyed. We just talked about this. We just talked about the conservation laws, the conservation principles. This is known as the conservation of energy. And importantly, we can use these principles and use a bit of logic to derive a mathematical formula for describing this. The second law is that the universe is lazy and that energy flows, and that there's this thing called entropy, which is typically described as randomness, but it's not always, doesn't always have to be randomness. And there's about at least 30 different ways of writing the second law of thermodynamics. The third law is that absolute zero is not possible. It's not possible to reach absolute zero because of the other laws. So applying the first law is going to be the most useful for chemical engineers, because we can write something called the energy balance based on the conservation of energy. Great. Should we write an energy balance? No, we're going to have to wait for that. Alright, now we talked about chemistry, we talked about physics, and then we're doing a crash course of everything you need for math. So, crash course. Number one, you need functions. What are functions? Input equals output. Pre-calculus, you're going to need the concept of the limit, concept of the differential, so we can derive concept of derivatives, the concept of integrals. Okay, so let's talk about these one at a time. So first we learn addition. In school, we learn how to add, and then we learn its inverse, subtraction. So we do like 5 plus 2, and then 3 minus 1, right? That's in grade school. And then we do multiplication. So multiplication is going to be, taking a sum of sums. So 3 times 3 is 9, and then we learn its inverse. 9 divided by 3 is 3. 27 divided by, 3. Then, as we get older in our studies, typically through grade school, we learn about powers. So powers are sums of multiplication. Hopefully that statement is true. But just thinking about powers, like 2 squared is 4, 3 squared is 9, 3 to the 3 is 27. So we learn all of those operations, and then we learn its inverse, the square root, the nth root, and then finally with calculus we learn about integrals and derivatives. Integrals and derivatives are typically described to be inverses of each other, but there is an even more beautiful relationship to integrals and derivatives known as the fundamental theorem of calculus. And using the fundamental theorem of calculus, and in combination with the concept of vectors and scalars, we can derive other really important theorems such as the divergence theorem and Stokes theorem. Those are really fun, really interesting. Okay, so functions are probably the number one thing that I want you to take away. Functions are just machines or computers or calculators that take a number and follow a unique set of instructions and display another number as an output. So we're going to have an input, and then we're going to do something in the machine and then process that number to produce an output. So let's do an example. If the function is x squared, right, the number that goes in is 1, and the output is going to be 1 squared, which is also just 1. If we have the input is 2, we're going to process that input, right, and then the output is going to be 2 squared, which is 4. So you do that again for any number you want. 3 squared is 9, 10 squared. Negative number, negative 14 squared, it's going to be 196. You can do that for any number x, the value x, okay? So if you plot all these numbers on the number line, on the x-axis you're going to have your inputs, and the y-axis you're going to have your outputs, and you plot those. You're going to have 1, 1, 2, 4, 3, 9, etc., etc. You put those on the number line on the x-axis and the number line on the y-axis, and then what you're going to do is you add more points in between. You add more points in between each of those. You go 1, 1.5, 2, 2.5.
You do those even more. You go even more in between. You do 1, 1.2, 1.3, 1.4. By the way, back in the day, without computers, they had to do this manually, one by one. But now we have computers to do this automatically, and we can take the limit as the distance between each of those points approaches 0. We're going to have a full picture of this function. So a function is just a graph. A function is just a machine or a calculator that takes a number as an input and follows a unique set of instructions and displays a graph as its output. Okay, so the input goes in, it's a number, the function is a calculator, and then the output is another number. And then the whole function is the whole picture, the whole graph. If you understand it, at least a fraction of these concepts, you can understand chemical engineering. Now we can talk about chemical engineering. So let's say we have, oh no, there's lots of typos here. Let's say we have a city, right? I'm going to get rid of this. Excuse me. Let's say we have a city, okay? And then 5 people per year come into the city, all right? And then 10 people per year leave the city, okay? And then inside the city, 10 people are born and 100 people die. So how many people, what is the net increase or the net decrease of people in the city? So 5 minus 10 plus 10 minus 100, that's negative 95. So in this city, negative 95 people are accumulating. That means 95 people are, that means there's a net decrease of 95 people with inside the city walls. So we have this equation. Did you see that equation on top? Accumulation equals in minus out plus born minus death. Okay, so what does that mean? So if we have this general equation, accumulation equals in minus out plus generation minus consumption. All right, this is the general balance equation. This is going to be your main equation for chemical engineering. So if you're doing mass balance, this is going to be your mass balance equation. If you're doing energy balance, you're going to do your energy balance equation. Accumulation equals in minus out plus generation minus consumption. So how would we apply this? Well, we can apply this to many engineering systems. We have the Navier-Stokes equations, application of momentum balance. We have the transport equations, application of momentum, heat, and mass flux balances. We can control our systems, derive control and dynamic systems. We have generation terms from kinetics. There's lots and lots to go over. But at the end of the day, I just want you to understand, when in doubt, accumulation equals in minus out. So you just add up everything coming in. Instead of your city, you're going to have a reactor. Or instead of a reactor, it might be a system, a tube, a pipe. Okay, so that's what chemical engineering is all about. When in doubt, accumulation equals in minus out. Okay, that's why SpongeBob is the best, because it's all about boxes. So when in doubt, accumulation equals in minus out. Alright, and I hope that you understand that if you take chemistry, calculus, and physics, you add up everything coming in, you subtract everything coming out, you mix that all together, calculus, chemistry, and physics. When in doubt, accumulation equals in minus out. You mix all those 3 classes together, you're going to get chemical engineering. My friends, what did I miss? What kind of questions can I help answer? I covered a lot. How many people are joining me? I'm going to start inviting, see who's down to join. So now I can answer y'all's questions. So if you guys have homework, what are y'all up to? I'm going to start advertising. I'm going to advertise to my friendsies, see if they need help on their homework. Do y'all need help on your classes? What classes are you guys taking? What classes are you guys taking? Are you guys chemical engineers? Or are you in high school looking, you're interested in chemical engineering maybe? or you're interested in general engineering. Do you think it's difficult? Do you think it's really easy? So I'm trying to cover a lot, and then over time I'm going to build this curriculum and make really fun, really nice application videos so we can make engineering as fun, as simple as possible. Alright, so join the live stream. Alright, and I'm doing office hours. Feel free to ask questions. I'm doing live office hours. If no one's gonna ask me questions, then I'm just gonna keep going, because after this is over, this is gonna turn into a video. So might as well just keep practicing for myself. So I'm going to continue talking about. I'm just gonna keep talking about dimensional analysis, because I said I was gonna be doing this for a while. So I'm going to talk about the first base dimension, which is mass. Okay, so mass is the first base dimension. We're going to have the fundamental equation for mass balance. We're going to have, when in doubt, accumulation equals N minus out. So this is going to be the next topic for today. And then as we move forward, I'll just continue to answer your questions, or just keep talking about chemical engineering. I can do this all night. Actually, I probably can. So mass is a fundamental base dimension that is a number represented by a scalar that tells you how much stuff an object has measured in kilograms. It is a proportionality constant to force that governs the inertia and therefore the motion of an object. Mass is not a force, and mass cannot be created or destroyed. So mass, we talked about it already. Mass is going to be one of the fundamental base dimensions. And so we're going to have the concept of mass. Literally just think of just the mass of an object, the mass of a heavy object. So mass is similar to force, but it's not exactly the same as force. It's going to be similar because it has inertia, but not particularly the same. Okay, we have some questions. I'm going to interrupt because now I'm going to pull up this final equation sheet right here. I'm going to talk about this because these are going to be your main mass balance equations. Okay, you're going to have your mass of your proton, mass of the proton, mass of the neutron, and then you're going to add up all of those. Alright, and then when in doubt, in minus out. So you're going to add up everything coming in. If you want me to go over more in depth with these equations, then I'll be happy to do so. Scholarships available. Okay, we can talk about money. Let's talk about money. We're going to make a new slide. Let's talk about money. Let me delete these. I'm going to make a new slide together. So let's talk about scholarships and financial aid. Okay, so what I did was I used Fafsa. Do you know what Fafsa is? Fafsa. So do you know what is Fafsa? Fafsa is the financial aid. What does Fafsa even stand for? I don't even know what Fafsa stands for. Fafsa. Free application for federal student aid. Free application for federal student aid. Okay, so this is going to be your ticket to get free money, free fellowships, and free scholarships. Okay, so this is what I used in undergrad, and then in grad school I also use this a little bit as well. So you're going to apply online. It's a very simple application, and then you're going to send in your records. Hopefully your school allows this. Hopefully the government in your country of residence also allows this, and you just get free money. You can also do loans. Okay, you You can also do loans. Not recommended. Not recommended. All right. Because loans are going to have interest. So try not to. I typically try to stay away from loans because loans have interest. And then we have other scholarships. Other. We're gonna have scholarships, and fellowships. So scholarships are gonna be just free money, just because someone trusts you, they're gonna give you free money, and then you don't have to pay them back. So loans are not recommended because you have to pay them back. You have to pay them back, sometimes with interest. So the best thing is going to be scholarships. So how do you look up scholarships? So with scholarships, there's going to be, you have to, first of all, just ask. So I only had I had two scholarships during undergrad. So I had a ask for available scholarships. So this might be academic based scholarships. It might be research based. Okay, so you're gonna have to ask maybe your professors, maybe I don't know who's gonna be in charge of those types of things in your school. For me, it was this gentleman whose job it was to look for these things, and then they send out emails. So you have to read your emails. And then see what are your qualifications. Honestly, if you see a scholarship, just apply. Because why? I just applied. There were 10 open they were gonna give away 10 scholarships, and there were only 4 applicants, so I was one of those 4. So they had 10 scholarships available and only 4 people applied, right? That happens all the time. So please, if you find something, just apply. And then you're gonna have to check online too. Check online for the best scholarships. So for me, I just used emails. That was my ticket in. Hopefully that answers your question. I know that was kind of vague because I was fortunate enough to have this person whose job it was to provide us with scholarships. Pull out my environmental homework. All right, you have a picture. So is this going to be like on Discord? Can you like post it? Can you post this somewhere? Post the picture. What kind of homework? See, I'm not really an environmental engineer. I do environmental research. So if you could post the picture, that'd be great. I can see what you're doing. Is it water treatment, water quality, water chemistry, air pollution? We'll try. I'll try my best. Any more questions? There's people like coming in and out. When in doubt, A minus out. I'm going to just say that currently now we're gonna do open office hours. Open office hours. Alright. I took a picture of your notes. I see. Alright. So how may I help if you have any specific questions? Oh, I think you're referring to this, right? Equations to calculate mass. Yes, please do screenshot all of this. These are also on my channel, so you can just straight up download the slides if you want. Check the links in the description. So I think what I want to talk about is the summation terms, because I kind of made up those equations. I kind of just made them up. So I'm going to talk about that now. So if I put I don't have private tutoring at the moment. I don't know if I should, because then it's going to be another investment, and it's a really time intensive investment. that I probably can't do at the moment. So if I do start doing it, it'll probably be by the time you graduate, by the time I graduate. So yeah, sorry, but I'll try to help out, because and I can try to like share like some videos and then help you guys out, and then it'll help me review as well. Yeah. Okay, but yeah, I'm gonna continue with this one though, because I think this is like really fundamental. So if you're watching this in the video later in the future, or just in the present, pay attention, because this is really fundamental. And then I'll put all the links in the description. So let's say there's a box, and then I put 5 balls inside the box, and then I take 3 balls outside the box. Obviously, it's gonna be 5 minus 3 is gonna be 2 balls left, right? Well, we're gonna replace that with kilograms of water. 5 kilograms of water minus 3 kilograms of water, same thing. Very easy, very straightforward. 5 minus 3 is 2 kilograms of water. So what you put in minus what you take out. Very simple, very fundamental mass balance equation. So what we're gonna do now is generalize it, and we're gonna say that the mass inside the box, mass in minus mass out, that is gonna be our fundamental mass balance equation. When in doubt, in minus out. But what if we make it a little bit interesting? We're gonna have a general. What if we have lots of things? We have water, we have orange juice, whatever we want. Just add like a lot of crap inside. You just mix it all up. It could be water, orange juice, methanol, toothpaste. It could be solid, it could be liquid. Just put up all those things inside the box. Okay, so the summation term, the big sigma, just simply means what is going to be everything coming in, and then you're subtracting everything that is coming out. So that's what those giant summation terms mean. So if we generalize that, we can also derive the continuity equation as well. So if you guys are taking your transport classes, we're going to do the limit as those values approach infinity, and then we're going to need some gradients, some divergences, right? And then that's going to be the limit. So that's why you see those summation terms. So all I'm saying with the summation term is you're just adding up everything, just adding up all those masses. Again, it could be water, it could be a solid, it could be a liquid, it could be a vapor phase. So chemical engineers are just using the principles of mass balance, conservation of mass, to derive those fundamental equations. Okay. I also want to point out, if I have it here, if I have like a number, yes, the number n right here, the number n. So n is very special because it's also another fundamental base dimension. It's moles. So moles is just number. So it could be number of atoms, right? Like Avogadro's number. So we have masses, density times volume, but we can also have number density. Okay, so now we can talk about concentration. That's going to be my next video. So concentration is just going to be simply mass over volume, but it could also be number density. So if you're studying your air systems, you can count the number of particles in the atmosphere, the number of particles, the number of contaminant particles in a stream down the line. Friends, what kind of questions can I answer? I love this interaction. I really do. Okay. Do you guys want to? So I said this is going to be said this is going to be a workshop. So do we want to build this dimensional analysis table together? We can do it together and see where we mess up. All right, we're gonna build this because I'm gonna be here for some time. So I'm gonna get rid of these. See if I can do it from scratch. Actually, I probably won't be able to do these from scratch, and I probably won't even need those anyway. Okay, but we're gonna say that mass is just gonna be m, mass, lowercase m. It's in kilograms, and the SI unit name is kilograms. All right. Dimension is capital M, and we said that mass is a scalar, right? The length is going to be any length dimension, so it can be in 3 dimensions, x, y, or z, and it's going to be in meters, and this is going to be meters. I'm going to say capital L, and we said that this is going to be a vector or a scalar. All right. Time is just time. I'm going to say the time is in seconds, so that's seconds, and we're going to say capital T for time. All right. That's just going to be a scalar. All right. And then let's add some more so we can fill this out. So I'm going to skip these ones because we're not going to use these. So let's start with the first one, mass flow rate. So mass flow rate is just going to be mass per time. So mass flow rate, I'll say, is mass per time. All right. That's great. So mass per time. And so it's going to be the mass flow rate is going to be the mass per time. So mass flow rate is just mass per time. How much mass, the mass flow rate. You know, it's kind of hard to define those circular logic because it's just the mass flow rate. So what the concept of mass flow rate is just how long does it take to fill up this hydro flask with water? How long does it take? How much mass per time? If it takes a minute, we calculate the mass of the hydro flask, the water inside the hydro flask. That's mass flow rate. All right. SI units is going to be kilograms per second. All right. SI unit name, doesn't really have a name. Okay, the question is this a vector or scalar? Is this a vector or scalar? It's going to be a scalar. The area. All right. So area is going to be interesting because it's going to be, now the area is going to be length squared. Length squared. So area is interesting because area can also be a vector or scalar. Okay? If you want, I can talk about that. Do I want to talk about area as a vector, or do I want to move on to something else? So I'm just going to define that area is going to be just area, and it's going to be equal to, area is going to be equal to delta x times delta y. Delta y. Right? It's delta x, delta y. That's the area vector. So I can define it as a scalar, or I can define it as a vector. Okay, this is just going to be, now this is going to be meters squared. Meters squared. All right. What's next? Volume. So volume is going to be area times delta z. Delta z. Right? Because volume is taking the second dimension and now you're extending it to the third dimension. So I think that's really fascinating. So that's going to be delta x cubed. So we can change this to delta x squared if you want, to make it really clear that the area is in the second dimension and volume is in the third dimension, right? Okay, that's going to be, oops, that's going to be meters cubed. Meters cubed. All right. And that's going to be length cubed. So volume, it's really interesting that in one dimension you can have a vector or scalar. And so a vector dotted with a vector is going to give you a scalar. But the cross product of two vectors is going to be a vector. So the area is going to be a vector. But a vector dotted with another vector is going to be a scalar. Okay? So if we want to talk about math, we can talk about some math. So volume is going to be a scalar for sure, not a vector. So volume is just volume. What is the volume of the hydro flask, right? Simple. 4th grade, 5th grade, middle school geometry. Just volume. Length times width times height. So that's why it's cubed. So volumetric flow rate is just like mass flow rate. Okay, so for some reason, some engineer back in the day said that Q would be a good idea for flow rate. I don't know why. They said Q would be good, and that's going to be volume over time. Alright, or we can do this dot like we did with the m dot, and we can say that Q is just going to be dotted V, right? So now what we have to do is we take the volume that we just derived divided by time. Alright, so the volume, what is volume over time? That's going to be length cubed over t. Alright, so a scalar, so volume is a scalar, divided by time is another scalar. So what is volume over time? Do we know? I'm going to let y'all think about that one for a little bit. Volume over time. And then this is going to be meters cubed per second. Alright? Alright. Speed. Okay, is speed a vector or a scalar? Alright, so we're going to say speed. Okay, I'm going to use V for speed, but I'm not going to put a vector yet, because we haven't defined our vectors properly in this video. But I'm going to say that V is our speed scalar. Oh, we have defined vectors earlier. So I'm going to say V is going to be your distance per time, right? Make sense? I'm gonna have to move this up. We're actually doing work. We're actually doing work on this. We're doing work. Alright. So speed is going to be length meters per second. Okay, so speed is just like how fast something is going physically in space, how fast it is. So notice the similarities between mass flow rate and volume flow rate and speed. So now we're combining everything in terms of rates. And notice how for rates, time is always in the denominator. So now this is going to be length per time. Okay, so speed is a scalar. Did anyone think about what is volumetric flow rate? Volumetric flow rate is also scalar. Alright. Velocity. So now velocity, what's the difference between speed and velocity? So velocity is a vector. Ha ha ha. Velocity is a vector. Vector B velocity. So now why is it a vector? Because we need to define the displacement vector, which we haven't done so. Sorry, physicists. Vector x over t. Okay, so now velocity is a vector, but it's also meters per second. It's also meters per second, and therefore it is also length per time. Okay, any more questions coming in? Nope. If no questions coming in, I'm just gonna keep going. So what is acceleration? Oh, also I'm going to differentiate this. If you want to be proper, to properly define the velocity, because now I can define the acceleration, because the acceleration is also a vector. So vector acceleration is going to be the time derivative of, oh, I don't like how Excel does that, dv dt, right? So if acceleration is the first derivative of velocity, that means it is the second derivative, the second derivative of displacement dt squared. Alright, so that's going to be meters per second squared. Okay, and then that's going to be length per time squared. Alright, let's keep it going. So what is momentum? Hopefully I can add more rows to this. How am I gonna add more rows? Insert, yes. Insert rows below. Let's add a few of these. This is beautiful. This is beautiful. What else can we do? Okay, so now momentum. Whoops. Momentum is gonna be is momentum a vector or scalar? Do you have any videos on engineering problems on Excel? Not exactly. I tend to. Oh wait, of course I do. Yes, I do. They're for solving mass balance problems. There's some of my recent videos. So if it has a little Excel logo, that means I use Excel. So let me go make sure that they're still there and stuff. Let me make sure. So if it has an Excel logo, then yeah. So go down the list. So check out the ones with the little Excel logo. With the Excel logo, and then if it has Excel logo, then that means I use Excel. So I think I have a couple of those videos. All right, and then of course I'll be happy to make more of those. Why do you need Excel for your homework? I'm sure you do. I also like using MATLAB or Python for solving your problems, because you're gonna have to do your projects, your design projects. You're gonna need lots of software. Great question. Okay, so now we're at momentum. So now momentum is going to be, oh, I gave it away. Momentum is a vector. Why is it a vector? Because it has an arrow. So the concept of momentum is mass times velocity, right? Mass times velocity. And that we already said what is velocity. So we said velocity is going to be dx dt. So do you see how we're combining everything? We're almost to force, which means we're almost to energy, which means we're almost to flux. Momentum is going to be now kilograms times meters per second squared. Alright, so that means that oh, not second squared. You're right. Just seconds. Alright. So it's gonna be mass times length per time. Okay, I like this. What's that to momentum? Force. Okay. So force is a vector. So let's type that in. Force is a vector. So force is going to be mass times acceleration. Mass times acceleration. Of course, it's also going to be the time derivative of momentum. So we need d momentum dt. Great. So what are those units? It's kilograms times meters per second squared. All right. Any more questions? Not so far. I'm just going to keep going. This is good practice for me. Mass times length per time squared. All right. So now things get interesting, because now we can talk about energy. So what is energy? Energy. Let's talk about work. So energy is going to be work is what? But the integral of the force vector dotted right by the displacement vector. Okay, so now things are getting weird, because now we need some line integrals, and so now that's a scalar. So the other day someone asked me why, what is the concept of pressure and energy versus density. So let's see. So pressure equals force over area, and force is going to be and energy is force times distance. So then it's going to be work per volume. So pressure is kind of like an energy density, as we'll see. Pressure is an energy density. That one, if I'm being totally honest, that one still confuses me. But hold on, I'm getting ahead of myself. So now this is going to be kilograms times meters squared per second squared, right? And then this is going to be mass times length squared per time squared. Okay, that's a scalar. Pressure is also scalar. In my opinion, that one's really confusing. That one's really, because pressure seems to act like a vector, like the force of pressure, but it's not. So we know that we know one thing. P equals nRT over V, right? Temperature from the ideal gas law, but it can also be force over area, or it could be work over volume. So pressure is really interesting, but always the units are going to be, you do the units, mass times, let's see, it's going to be mass per length per time squared, right? How am I doing this? Because it's going to be mass times length per time squared times length squared, mass per length per time squared. All right, does that make sense? Cool. So whether you're watching this in live or in the future, we just finished deriving the entirety of the, well, not the entire thing, but a huge jumbo of dimensional analysis, all the functions we need. So now we can do anything we want. We can talk about vectors and scalars, we can talk about fluid mechanics, we can talk about mass balance, we can talk about energy balance. So we can go anywhere from here. So if you're like in high school and you're barely starting chemistry and physics, then this is kind of going to be like a lot of what you're seeing. Mass, length, and time everywhere. We didn't talk about temperature too much. We didn't talk about electric current, so I skipped over these. So we don't deal with these too much. But we have all these other quantities. All right. We can keep going. We can talk about flux. Let's do one more. I'm going to do flux. That's the last one. So flux. Okay, let me make another slide for this, because this is going to be about flux. Flux is going to be amount per area per time. All right. So if we want to do mass flux, that's going to be mass per area per time, and then we just copy paste that. Momentum flux, right? Momentum flux is going to be momentum per area per time, and then heat flux is going to be heat per area per time. So flux is just going to be how much stuff is going through the wall, how much stuff is going through the door. You're just counting out, how much stuff, like light, particles, heat, or people are going through the door. Going through the door. So if we want, let's draw a door, right? We're going to draw the door. Let's just put the door right there. There's the door. Good. That's the window. No fill. Shape outline. Black. So we're gonna count how many. Can I shear this to make it look like it's 3D? I want to make this. No, I want like a 3D box because we're gonna need 3D figures. Yes. Right here. Yes. All right. So now we're gonna put this. All right, and then fill this box. Count how many. Let's put some arrows. That's the door. Count all these arrows. Just count them. Those are all the flux. Those are all the vectors. So it can be an open system. It has to be an open system, and then we're just gonna count them all. Y'all, I think we did a lot for one day. I think I'm gonna leave it at that. If you have any questions, please definitely check out the rest of my videos. And then let me know what you think of this live stream. We can like change it up. We can do more office hours. We can do more workshops. Whatever y'all want. And then it's going to be here forever. So if you miss this one, it's going to be here forever. It is a long time, but remember the first hour is just doing a study with me. So I think I kind of like that, at least for me personally. I don't know about y'all, because it was good for me to just literally just study.